Doreen, it's okay. Florence, it's okay. I can start.
Yes, you can start, Martina. Please, over to you.
Okay, thank you so much for the third day of summer school, newcomer summer school, newcomer for nuclear summer school. It is a great pleasure for us to welcome you for the dedication for the nuclear science for nuclear technology. Today we have Ya has a moderator, Yas Anima Ampare Apia. She's a Apia is a PhD student in material science and engineering at Penn State University with a strong research focus on nuclear material and waste uh, immobilization. She previously served as an assistant research officer in nuclear material accounting at Ghana's Nuclear Regulatory Authority, and also advances degrees from CUNET, Benjin University of Chemical Technology, and IES and IEA program in radiation protection. At 2023 Schlumberg Faculty for the Future Fellow and Vice President of WiNI Penn State, Ya is deeply committed to equity education and nuclear proliferation. She actively mentors emerging women in STEAM and leads a community outreach effort to promote nuclear literacy. Among underrepresented youth, he worked bridge technical innovation with advocacy aiming to shape a more inclusive and globally connected nuclear future. He also currently serves as the vice president of WiNI Pennsylvania State, as well as the networking chair of Penn State chapter of the Institute of Nuclear Material Management. You have a floor to present your speaker and to start the session. Thank you so much.
Thank you, everyone. I am so elated to be here this morning, this afternoon, this evening, depending on where in the world you are. Thank you and welcome to this session of Newcomers for Nuclear. I hope you enjoy this session. If you have been joining from day one, you know that this is a very worthy course. This is a platform where we learn and share together. And I am so honored to be your moderator or co-moderator for today. So please allow me to introduce our first speaker immediately. We are not going to waste any time. Our first speaker for today is Doreen Abesundra. You'll be marveled at what Doreen has already achieved in her life. Doreen Abesundra is the founder and principal of Fresco Clean Tech Solutions, and it's an independent financial consultancy which offers innovative, bankable financial structures for project developers, owners, and investors to incentivize investment for seed, equity, and long-term debt financing. If you've been anywhere along the nuclear chain, you know that debt financing is a big issue for us, and Doreen Abesundra is at the forefront of it. She is an astute financier and advisor with debt and equity investment experience for corporate and project financing, plus power purchase agreement negotiation in nuclear, onshore and offshore wind, hydrogen, and circular fuels. She holds an MSc in climate change management from Birkbeck University of London. She is a first-class pass in the Said Business School, Oxford University FinTech program, and has attained ICAEW's non-executive director certification. Doreen, you have a marvelous profile, and I can't wait, alongside all the others joined here, to hear what you have for us today. Please take the floor.
Brilliant. Thank you so very much to everyone who's worked so hard to put this together, and a real credit to you guys for creating the idea to make it online, in particular to open up the conversation to everyone globally. So as shared, my name is Doreen Abisundra, and I run Fresco Cleantech Solutions, which is an independent financial consultancy that is focused on structuring and securing financing for new nuclear in particular, along with the derivatives that we will start talking about. I just want to make sure that you can see my slides because I am sharing it, and you should see a disclaimer on the screen right now. Can someone confirm that?
You can see the disclaimer.
Brilliant. Fantastic. So obviously, I have to put out a message that everything I say here is just an opinion that I'm giving you, and any sort of thoughts that come from the result of this is, something that I'm happy to talk through with you as an independent consultant. But obviously, take your own advice and please make your own decisions. So what does Fresco Cleantech do? As I mentioned briefly, it's an independent consultancy. I put the tagline to myself that I'm a recovering banker. I spent quite a number of years doing project financing here in London, but for across the Europe, Middle East, and Africa region. And the idea has been to transfer all that knowledge brought in from financing large, in particular energy projects, to the nuclear space. And the focus for Fresco Cleantech is to focus on decarbonization, the advancement of AI, and obviously energy security, which, as we know, is becoming a very big topic these days. Now, nuclear power is very, very is utilized in very many ways. We had the real privilege of listening to some of our colleagues yesterday talking about how nuclear can be used in medicine, right across to alternative uses. But I'm going to focus on energy for this particular discussion. Is nuclear new to energy? I think the answer is very clear. No, it's not. I was surprised to see that actually it's 372 gigawatts of nuclear power that is currently being harnessed for generating electricity in particular. There's a whole range of financing structures that we can talk about. Why should we look at nuclear energy? Well, apart from the energy security, the low carbon emissions that it provides, it's a new and exciting technology. It's going to be providing lots of employment opportunities as well. And then I mentioned derivatives. We're going to start looking at how nuclear power, not just for the electricity, but that how it can be used to generate the manufacture of SAF, which is sustainable aviation fuels, how we can combine it with direct air capture, and also to harness it within maritime. So I'm conscious we only have 10-ish minutes for me to do the presentation. So I'm going to really run through very quickly, but when we come to the Q&A, more than happy to take questions, and obviously we can chat thereafter. Putting out lots of information on this slide, but the key message is that there is an active need to increase the use of nuclear for electricity generation. I think everyone has heard a lot of conversation about AI. AI is almost a byword, a buzzword these days, but the one clear message that we should take away from what the International Energy Agency says is that there won't be any AI if we don't have more energy, because they work hand in hand. One of the key things that is needed to generate AI and its advancement are data centers. I think I don't need to ask you to tell me more about data centers if that's coming up in conversation. I'm sure throughout the globe we are seeing data centers. And bear in mind, every time you use your phone, whether it's looking at videos of cats dancing around on TikTok or doing a real research on, how we can use nuclear, all of that requires energy. It all goes into a data center for processing, every time the data center runs a request, it needs electricity. And of course, cooling, that's going to be a subject to discuss on the side. But in general, the IAEA, which I'm sure all of you must know now, that's the International Agency for the Atomic Energy Association, that is, the IAEA is predicting we are going to need perhaps 2 or even 3 times of the energy needs, plus also that we're going to be seeing that that graph, that exponential increase of nuclear projects to fund that, to provide the energy that's needed for the nuclear generation. Now, where are we seeing the biggest market? The biggest market is the US right now. There is what I call the gauntlet has been thrown down. The challenge has been thrown down for us outside of the US. There are nuclear and the reactor technology program to try and bring out new technologies. And the aim is to get new nuclear operational at least by 3 different technologies by next Independence Day, which is July 4th. So we've heard many discussions about what new nuclear is. By the way, the so-called older nuclear is the gigawatt scale projects that we see throughout the world in many different continents. New nuclear says that we're going to take perhaps a new way of looking at generating the nuclear facility. It's called advanced nuclear. It usually is everything from generation 3 plus and above, typically generation 4. Generation 3 is fission, and generation 4 goes beyond fission to use perhaps molten salt. Sorry, I should say they're all fission, but in terms of generation 4, it's using perhaps different types of fuel, different types of coolants. Again, running through, but the slide will show the various different kinds of technologies that's being created with new nuclear. And I'm drawing this attention to you because all this needs financing, all these needs jobs, all these needs understanding, and all of these need scientists all the way across to students to understand and contribute to the technology that is developing. So it's not too late to get onto the bandwagon. From a financing structure, what do we always need to look at? I think, and obviously my caveat, always seek advice if you're looking to put together some financing, but the general concept is that we can finance things in 2 rough ways. And there are lots of words on this slide deck and a big picture there, but let me ask you to visualize the apartment or home that either you or a member of your family might own. How do you go about getting a home? Very often, the bank will say to you, I need you to provide at least, say, 10% of your own money. That's equity. And then the bank will say, then I will give you the remaining 90%. That's a debt. Any sort of project, even if it's very complicated, I ask you to look back at a very simple concept of a mortgage. And of course, if you've got a family member or cash in the bank and you say, I'm just going to buy that apartment or home 100% with my own money, then 100% equity is yours. And so nuclear projects have been financed in a combination of these ways, mostly a combination of part equity, often provided by government, and debt provided either by a government, or now we are seeing more commercial lenders coming into the market for debt. I wanted to emphasize the concept of a regulated asset-based model. Go have a look at it by a quick search, but that's something that we've done here in the UK, where we do that combination of public-private partnerships. Again, running through terms so that it just sits in your head and we can always have a follow-up conversation. This is a slide I put together just to give you a sense of how you structure a financing. You know, we often hear the word seed, VC, equity, as we just talked about, mezzanine. Where does it all sit? It sounds very complicated, but if as I mentioned before, start thinking about how you finance something as basic as a home or your bicycle or your car, you have to put a combination. So a seed or a VC could be, You know, if you're a student and you've got mom and dad helping you out, or a guardian that says, here's $10 towards that purchase of a bicycle you want. That's your seed funding. That's the very initial stages that helps you get to a point that says, maybe I'll get there. And then, of course, we spoke about how equity and debt is focused. Again, very, very simple, basic concepts, but of course, it gets more complex when it gets to nuclear financing. So some of the key considerations when it comes to either financing one of the so-called gigawatt scale projects or one of the new nuclear facilities, some of them often known as SMRs, small modular reactors, or advanced modular reactors, they perhaps might need fewer billions of dollars, but even 1 billion is a lot of money to raise by anyone. So we do that combination of equity and debt, but the things that you always need to look out for is there a site? Is there permits for me to get the nuclear plant up and going? Who are the shareholders? You know, we talked about the equity. Who else is going to be there to provide the debt? Obviously, when it comes to new nuclear, we have to start thinking ahead of time, even today when we're starting to finance it, by thinking, what are we going to do with the spent fuel? That means the nuclear, the radioactive waste. Or how are we even going to decommission the facility? Because it's not a simple project where you can just take it apart and say, well, let's put it in a landfill. Obvious reasons. The other things to consider are always something called due diligence. One of the key due diligence you need, financial advisory, due diligence. Second one, legal, insurance, and ESG, so environmental and sustainability governance. But don't forget to add cybersecurity. These days, cybersecurity is something that's vital, not just for financing of nuclear, but I encourage you to even look at the cybersecurity of even if you're putting a solar plant together in terms of financing or even your own projects. Because what you want to know is that you've got some sort of malware kind of protection. Keyword digital twins. Maybe do a reaction if you know what digital twins is. Put a little heart or a star or something so it comes up. Okay, so then digital twins is really making a copy, an online software copy of a project, not only from the construction, but also from the financing. I encourage you to look up digital twins and use it. It's literally, you know, in the old days when you had to build something, you go and get some paper mache and put together and say, what is it going to look like? But this, we're doing it with a more complex, sophisticated way online, often with AI. We spoke very briefly about data centers, one of the big users of energy these days. I put in a picture thanks to NVIDIA and XAI. You know, let's visualize where things are going to go. We're going to need this huge project for data centers. We're going to need a huge plot of land or a small plot of land if you're using an SMR. But in every sort of data center needs continuous power, backup power, cooling, as we mentioned, and a connection to the grid. Or what behind the meters means is that you've got just one energy source that you literally plug in to your data center. And you can replace data centers with any sort of high intensive energy use. For example, a cement factory. What we need to do is decarbonize. That's the key message. And I'm running out of time, but I wanted to just take 1 minute and say, using all the terms, and this is a kind of privilege I'm using as your speaker, I encourage everyone speaking in because I recognize this is a newcomer, so we can have lots of students, lots of young people, or people that are just getting back into the workplace. I encourage you to always understand debt, equity from your own perspective. Understand where your pension is. Even if you're 24 years old, think about in 30, 40 years time, if I make the same amount of money today, how much will I have when I start becoming 50, 60, 70? Very important. Use all these terms that we're doing to finance a nuclear plant with financing yourself as well. So this is my profile. Very much happy to take questions and either here or follow up thereafter.
Yeah. Thank you so much, Doreen. It was such an insightful session. We have a few minutes to take a few questions. And so we invite you to raise your hand so we can know who wants to ask a question. But I want to go first. I'll veto and give the first question. So I wanted to ask, Doreen, how did you decide that you're going to take the step and start a business in nuclear financing? I'm wondering was it a spark or something? Did you notice an issue? What happened?
Thank you, Yomina. That's a fantastic question. The very first time I thought about running an independent financial consultancy was after I left one of the big banks that I used to work for a decade. I saw very often that from a big bank's perspective, we were advising the big companies of the world. But as decarbonization is progressing, we're seeing new technologies coming on. When I first started it, some of the new technologies included something we call green hydrogen, which is hydrogen manufactured by renewable energy or even floating offshore wind. And those smaller developers needed to have the exact same information and knowledge on how to structure a project. So whether you're doing a $10 million project or a $1 billion or a $10 billion project, the financing thoughts behind it are the same. You know, that debt equity breakdown and the thoughts and risk considerations to consider. And so that got me thinking, why don't I provide that from an independent perspective where I can do it at my own pace, but also work and collaborate with who I want and who I see a need to help support. It's been a brilliant journey, and I encourage everyone to do it, albeit it's not always you can't slack off, that's for sure. So when you've got your own desk-bound job and you think, oh, I'm just going to take an extra hour for lunch, you're just walking into your own profits in that sense.
Thank you. That's a good answer. So now I know where the inspiration came from. There's a question from Idrissa Wedrago, and she's asking, in the context of radiation protection at nuclear power plants, how can we ensure that the effective doses assigned to workers exposed to... Oh, I think this is not for you because it has nothing to do with
Well, yeah,
financing.
sure. It's more a technical
So I'm
question.
going to
I was
leave
going
it
to
here,
answer it from the
and then
basis of it.
the
Yeah.
experts for radiation protection can take it up.
Yeah, and exactly. So you're right. That's not for a financier to directly give you the real answer. However, from a financing perspective, if you remember, I said before, always do your risk considerations and due diligence. Technical due diligence is fundamental. And so from your technical due diligence, your ESG due diligence, we'll get those answers. And those are fundamental questions to be answered in order to make sure the financing goes hand in hand. So in a way, it's a very good question to ask because you can see that financing is not just saying, oh, I've got $10 billion to lend or $1 million to lend. I need to understand everything to make sure that works.
All right. Thank you so much. And now we are going on to the next speaker. But before then, I'd like to request everyone to put on their cameras for a few seconds so we take a group picture. And then you can beat with your chest and say that, oh, I was a part of Newcomers for Nuclear Day 3. Please put on your cameras.
While everyone's putting on the camera, I wanted to just pick up, you asked me the question specifically about consulting in nuclear. And I wanted to say to you, Amina, that the specific reason why I now focus on new nuclear is because it's so exciting. There's so much to do. You saw all those opportunities in advanced reactors. So it's a very, very exciting topic, very open to everyone.
I have many people whose cameras are not switched on, but we'll make do with what we have. Oh, Mr. Enobot, welcome. Are you ready?
I'm ready.
One, two, go. Okay.
Let's check the settings after the presentation of Mr. Enobot. And let me just check back the settings that everyone get the permission to open their cameras.
By the way, there is a background sound. I'm not sure if you can hear it. There's someone like a radio in the background. It's just so you know.
Let me see. I think now would be better, right? Yes, I think so. So yeah, let's just get into the next presentation, and then we just talk quickly about the camera issue for the rest of the participants.
I totally agree.
Thank you.
Okay.
Next speaker is Mr. Onobo. Mrs. Aissa Diallo will be moderator, and after you have to continue for the last speaker. Larissa, that is true?
Next speaker is Mr. Enobot. It was an unexpected change because Doran was supposed to finish the day of today with the session, but Mr. Hallead has been moved to the last slot of the presentation. So let's continue with Mr. Enobot.
Okay, the moderator is Mrs. Aissa Diallo.
Aisata is around.
Yeah.
She can co-moderate with Land, and we get back to you as well. And get back to Mr. Thank you.
Okay, thanks so much. Our next moderator is Aissa Diallo. She's a member of Young NewComers4Nuclear of Burkina Faso. She's a student in mechanical and production engineering at Nazi Boni University in Bobo Dioulasso, the second time of Burkina Faso. She's also active member of a WiNI association in Burkina Faso. Miss Aissa Diallo, you have the floor to present your speaker and to take the lead of the rest of the presentation of the session. Thank you so much.
Thank you, Monsieur Lassina, for the floor. Good evening, everyone. I am Aissatou Diallo, and I will introduce our speaker for this session. Our next speaker is Mr. Enobot Akboro, the Executive Secretary of AFCON, the African Commission on Nuclear Energy. She will talk about the future of nuclear in Africa. Mr. Enobot, you have the floor, please.
Thank you very much. Can you screen my presentation?
Yes, please, just a few seconds.
Thank you. I would like to thank the organizers of NewComers4Nuclear. This is a very good initiative to promote nuclear, not only in Africa, but across the world. And let me thank the newcomers who are present in this meeting and the recomers that are already old in nuclear. The next slide, please. When we talk about nuclear energy, we refer to different things. the energy that comes from nuclear reactions in the atom can be used in medicine and industry, in agriculture, and various applications. But the application that I'm going to focus in this presentation is the production of electricity with nuclear energy. And the reason for that is because I believe that this is the most, or one of the most urgent nuclear applications for Africa. Because if one has energy, then one has the engine to drive all the other applications and to do all the other things that we need to do to improve the socio-economic situation of our people. Next slide, please. Africa is often called the dark continent, and that's because of the skin color of most Africans. But Africa is literally the dark continent from the point of view of electricity. That picture we have on the screen is a night view of the world. And you can see that Africa is mostly dark. There's a little bit of light down in the south, a bit on the west coast and in the far north. But everywhere else looks dark. There are some dark patches on other continents, but those are deserts and areas that are not inhabited. But the dark areas of Africa are areas that are densely inhabited. So that's something we need to think about. The next slide, please. So this table is a table of electricity production per capita. And if you look at the bottom in red, that's the electricity production per capita in Africa. It's about 0.38. And if you look at the other parts of the world, it's clear that there might be a good correlation between electricity production per capita and industrial and socio-economic development. The next slide, please. So in this slide, I wanted to tell some stories. My 4-year-old granddaughter visited an African country recently with her mother. And I met them last week. And she was excitedly telling me about her trip to Africa. And one of the things she said is that in Africa, she noticed that the lights turned themselves off. And I thought, wow, the innocence of children. Only a child can put it that way. The lights did not turn themselves off. I mean, what happened is what is called different things in different places, outages, load shedding. But I thought that's a very interesting observation. And a neighbor of mine lost her life recently in Africa. And that's because she was on an oxygen machine at home. And when power went off, she did not have her phone nearby. And before she could get help, it was too late. And these are the types of things that happen when there's energy poverty. The next slide, please. I think, did you skip a slide? Anyway, it doesn't matter. I will. So the question I wanted to ask before the slide was, is there a need for energy in general in Africa? Yes, for the reasons that we've just gone through. And why nuclear power in particular? So I listed 5 things. I'm not going to speak about all of them, but during the question and answer, I will be happy to speak about any one of them. So on this slide, I'm going to speak briefly about number 1 and number 2. Climate change. It's been established that there will be no net zero globally unless there's energy transition in Africa. So that's a fact. So, and in order to combat climate change, we need to move to sustainable energy, to clean sources of energy that put a low amount of carbon dioxide and other climate gases in the atmosphere. So we need nuclear as one of the clean energy sources, and also because, and nuclear in particular in Africa, because of the impact it would have on net zero globally. And the other reason now I'm talking about number 2 is energy security. And energy security comes in many guises. The guise I want to speak about here is nuclear energy is a clean source of energy that is not prone to climate. All of the others are prone to climate in the sense that solar is intermittent, wind is intermittent, and even hydro is intermittent and prone to climate in the sense that when there's no rainfall, there are issues with hydro. And climate change is affecting water resources. So in my book, hydroelectricity is a clean source of energy that is prone to climate. The next slide, please. So in the other slide, I said that nuclear power is cost to the consumer in the long term. This picture, I copied it from the 2024 annual reports of Eskom, the electricity company in South Africa. And if you look at it, the cost of electricity from nuclear power in South Africa per megawatt hour is 113 rand. That is about $5. It is so cheap because nuclear power in South Africa comes from the Kruger nuclear power plant, which is over 30 years old now, and the capital investment, which was very high, has been paid. So in the long term, once the capital investment for a nuclear power plant is paid, the running costs are very low, and to a large extent because of the energy density of the fuel. If you look at, open cycle gas turbines, we're looking at $30, over $30 per megawatt hour. And renewables are also, what are the renewables? $10 per megawatt hour, not $10, almost $50 or something like that. I'm not doing the conversions well, but if you look at that, you can see that nuclear power is actually dead cheap once the capital investment is paid off. The next slide, please. So does nuclear power have a future in Africa? Yes, obviously. There's no doubt about that. For climate change reasons, for energy security reasons. And I just point out something here, I might speak about it later. But say you compare nuclear power with one of the other clean energy sources, let's say gas, natural gas, and let's say 1,000 megawatts. It would cost, maybe rule of thumb, say $10 billion to build a nuclear power plant, over a period of, 6, 7 years. It would cost maybe $1 billion to $2 billion to build the same gas power plant with 1,000 megawatt capacity. And you start, making profits much quicker. But the cost of running the gas plant is very high compared to nuclear. And like I showed in the previous slide, once you pay off the capital investment, then nuclear is cheaper. And another thing is that the lifetime of a nuclear power plant is about 80 years these days. And it's with technology going to be longer. With these other technologies, you have the lifetime of, 20, 25 years. So when you're comparing cost, I think to be fair, you have to compare the cost of all the other plants that would be built during the same time period that your one nuclear power plant is still operating. And nuclear power, provides more energy security in terms of sustainable development. Sustainable development is normally defined as doing something that would not hurt future generations. But you can also look at it the other way, that doing something that would help future generations. So when you have a nuclear power plant that lasts for about 80 years, you know that your grandchildren and your great-grandchildren will have power. But with some of the other technologies, nobody knows what will happen in 20 years, 25 years' time, what the geopolitical situation would be, what kind of economic climate we will have, whether one would be able to build another one. So once you build the nuclear power plant, you don't worry about building another one for almost a century. And that's another aspect of energy security. The next slide, please. So these are the hurdles. I've already mentioned some of them. Capital investment is high. Many infrastructure issues to take care of. Public perception that is mostly not positive. Proliferation concerns. And I say energy poverty because you do need energy to build energy. So there's a kind of a chicken and egg there. And I think in Africa, there are cultural issues that we must overcome to get things to work better. The next slide, please. And how can we go about expediting the deployment of nuclear power in Africa? And there's so many things that one can do. But here's a list of 7. Regional cooperation, stakeholder engagement is important, infrastructure development, funding and financing. We heard about that. Are we going for SMRs or for the traditional big builds? What are our non-proliferation credentials? And like in the previous slide, I said we need a cultural revolution. I will speak briefly about number one, regional cooperation. To build the nuclear power plant, a lot of money is needed. And the banks need guarantees that the borrower can pay back. And most countries in Africa are poor countries and are deep in debt. And that does not provide confidence to lenders. There are also political issues, political risk, and proliferation risks that we saw in the previous slide. And I think that if groups of countries band together to develop nuclear power together, it gives more confidence to lenders because there are more guarantees against the loan. There's more immunity to political and proliferation risk. And in fact, we are moving towards a world that is about regions as opposed to countries. And I think the way that the world is organized really depends on how technology is flowing. You go back in history, our communities were based around villages because there was no real communication between villages. There was no transportation, there were no telephones, there was no way of people getting together. And as technology grew, we enlarged into towns and into countries. And now with digital technologies, one can even say it's a global world, but let's stay with regional for now. And I think one of the most important things that should be done to expedite the deployment of nuclear power in Africa is regional, because most of the countries do not have the expertise or the infrastructure or the human resources to do it by themselves. But together, pooling our resources, I think we can do it, even in terms of funding and self-financing. It can be done. If you look at the example of the dam in Ethiopia, that's a funding strategy that one should pay attention to. The next slide, please. That was it. I'll be happy to take any questions.
Thank you very much, Mr. Enobot, for this insightful presentation on the future of the nuclear in Africa. Among the key points we can retain the prospect of nuclear energy on the continent, the type of nuclear power technology to adopt, the factors that can hinder or enable nuclear power in Africa, and finally, the cultural outlook which remain a non-negligible factor in shaping how nuclear power is perceived and implemented. Now we will take some questions. If you have a questions, please write it in the chat. We have a question. Mr. Enobot, here is a question from the audience. That are the main financial challenges of development nuclear power in Africa?
the financial challenges is the capital cost of building a nuclear power plant and the difficulty of the financial of countries with African countries with the financial profile that they have to get funding. And that is why for many years, most of the multilateral development banks have said they will not finance nuclear, not even in Europe. So to develop nuclear, it is very important to think about how, to what extent you can finance it yourself. That was the equity part we heard in the previous presentation. I gave the example of Ethiopia, the big dam that they're building. The banks refused to provide loans to Ethiopia, but this dam is very important to them. So they're financing it themselves to the tune of about $6 billion through funding, which is usually free money from Ethiopian citizens and those in the diaspora, and from selling government bonds. So this $6 billion project is going to be self-financed. And let me give another example we have this in many African countries where the banking system is not very good. Family groups and groups of friends meet regularly and contribute money, and it goes round and round in a circle. This is something in our culture that we can use. Let's take an African country with, say, with an employment rate of, let's say, 50%. And let's say that 50% amounts to, say, 30 million people. And let's say about 20 million of those people make a commitment to pay to a government energy fund $100 a month. You can calculate yourself how long it would take to save $10 billion. Not too long. Africa has 30% of the world's mineral resources. If we do a regional approach and we work together, we can leverage those mineral resources to pay for nuclear power. So there are all kinds of mechanisms that we can take advantage of. And we do have finance experts like the previous presenter that we can work with. That's the end of my answer to that question.
Thank you for that insightful. Now we moving to the next questions. The audience asked, why are the main barriers to developing nuclear in Africa? Financing, social acceptance.
Well, two things quickly come to mind. The first one is lack of sufficient awareness. I have been in meetings where African countries have sent people from the military to discuss civilian nuclear infrastructure. This is because there's a certain perception that nuclear has to do with weapons, with bombs. And this is because of what happened in Hiroshima and Nagasaki during the Second World War. And I remember when I was leaving home for the first time, I was 12 years old and I was going to a boarding school, secondary school. And my father said to me, you have to lay a good foundation. This is your only opportunity to do that. And if you don't do that, you're going to struggle throughout. And laying a good foundation means the same as giving a first impression. The introduction of nuclear to the world, unfortunately, was mostly through the bombs. And that created a bad first impression for nuclear. That's one of the reasons why we're still suffering in terms of public perception, even in Africa. Another issue that we have in Africa is the issue of waste. People talk about nuclear waste. It depends how you look at it. But in a certain sense, spent fuel is not your normal, it's not waste in the normal sense of the word, because spent fuel cannot be dumped, for example. And spent fuel is actually a resource that will be fuel when we start using more advanced reactors based on fast nuclear reactions in the future. And another issue with waste in Africa, I think, is you can call it emotional, because in the 80s, foreign companies dumped chemical waste in Africa. And that is what pushed the Organization of African Unity at that time to promulgate the Bamako Convention, which is actually in many ways an impediment to the development of nuclear in Africa. And so many Africans have waste as a taboo, and they don't want to speak about nuclear waste in inverted commas. Well, it's like you want to build a house, but you don't want to have anything to do with the toilets in the house. So how's that going to work? You know, if we are serious about having nuclear power to address the energy poverty and to drive our industrial development, then nuclear waste is a topic that must be part of regular discussion. That's the end of my answer to that question.
That is very interesting. Finally, questions. Are Africa countries considering specific countries to support them in starting the nuclear PPTS?
Sorry, I didn't understand that one.
So, but I think for your session, there are so many people who want to ask you so many questions. So I would encourage everybody to write their questions in the chat. Mr. Enobot will answer them, and then we share it with everybody across board so that we keep in time. And Mr. Khalid Mahmood can also give us his prepared slides.
I'll be happy to do that.
Thank you.
For
Thank you so much for
me.
your time. Aisata, thank you. I enjoyed your session so much. Okay. On to the next expert. I am so sure you are going to enjoy Mr. Khalid Mahmood. Oh, before I even introduce Mr. Khalid Mahmood, please let me bring to mind that recently the WiNI Pakistan chapter was officially launched. So if you're anywhere in Pakistan, if you're a Pakistani, whether man or woman, please be sure to join Women in Nuclear Pakistan, because we need your support. We need both the women and the men support. Right now, let me immediately zoom into introducing Mr. Khalid Mahmood. Mr. Mahmood is a highly accomplished and results-oriented health physicist and principal radiation protection specialist with over 12 years experience in the nuclear power industry. Proven expertise in operational health physics, radiation protection, radiation safety, radiation monitoring systems, radioactive waste management, and emergency preparedness. Demonstrated success in developing and implementing radiation protection programs, radioactive effluent control programs, and radioactive waste management programs in compliance with both national and international standards. Mr. Khalid Mahmood is adept at leading teams, managing radioactive materials, including radioactive waste, operation and radiation monitoring systems, as well as conducting radiological service and risk assessments, and ensuring the safety of personnel and the environment. Seeking a new challenge to grow further in his field is what he is about nowadays, and he is eager to share his expertise with us. Mr. Khalid Mahmood, please take the floor. We are eager to hear from you.
Thank you so much for such a nice introduction. And I have prepared a lot of slides because there was confusion regarding my time slot. So I will quickly move towards my presentation and start doing the business. I am sharing my screen. Please confirm that has it been shared? Can you see my screen?
Yes, we can.
Okay. Let me move to the slideshow mode. Okay, here we go. So the topic of my presentation is the radiation protection at nuclear power plants with focus on RP principles, radiation sources, how to control, and the best industry practices in radiation protection. So this is my presentation layout. I'm going to discuss what is radiological protection, what are the ICRP, principles of radiological protection, what are the ionizing radiation which are encountered at nuclear power plants, what are the sources of these radiation which generate the radiation field at nuclear power plants, radiation dosimetry, radiation dose limits, and the very important ALARA principle, radiation exposure reduction techniques, that is the internal exposure reduction and the external exposure reduction techniques at NPP, radioactive contamination control at NPP, radiation zoning, posting and labeling at NPP. At the end, I'm going to summarize with the references from which I have developed this presentation and general references to use in the field of radiation protection as a resource. So this is the schematic diagram of a typical pressurized water reactor. There are three loops. In the containment structure, we have primary loop. Primary loop means that there is a reactor, we have control rods, reactor core containing the fuel. The water acts as a coolant and runs through the fuel, takes its heats, and gives it heats to the feed water in the steam generator via steam generator tubes, gets heated, converts into steam, goes to the turbine, rolls the turbine, turbine then rotate the generator, and the generator then generates the electricity. The steam in the turbine goes to condenser, where it is condensed, and its heat is taken by your cooling towers, and the cooling towers give their heat to the reservoir. So each loop is isolated from the other loop, so that the radioactivity, there are layers to the release of radioactivity from one loop to the other. Whole of the reactivity, whole of the activity is contained in the nuclear fuel, which is in the containment. So containment acts as a primary boundary against the release of radioactivity to the environment. So the radiological protection at nuclear power plant is integrated into all phases of nuclear power plant. That is the design phase, the operation, the maintenance, and the decommissioning phase. It focuses on controlling exposure to workers, public, and the environment through measures like chemistry control, like monitoring, surveying, shielding, administrative measures like radiation work permit, special radiation work permit, high radiation area, lock and key controls, using regulations, international standards, and industry best practices. The key goal here at nuclear power plant in the context of radiological protection is to prevent the deterministic health effects of the ionizing radiation, that is, for example, radiation burns, arrhythmia, and reduce the probability of stochastic risks like cancer and hereditary effects using the as low as reasonably achievable ALARA principle. So how ionizing radiation from NPP affects workers, public, and the environment? Workers get direct exposure during the maintenance outages due to the activated components, or they get internal exposure via inhalation, ingestion in the contaminated areas. Public do not get the direct radiation exposure. However, the effluents released from the plant in gaseous and liquid form may cause negligible radiological risk to the public. However, in the case of accidents, the fallout can cause thyroids and severe radiation damages. The environment can be contaminated, contamination of soils, water, ecosystems, biodiversity, food chains, long-term effects on the biodiversity. So the scenarios in which the public, the workers, and the environment can get radiation exposure are normal operations, during normal operations, low doses, during accidents, high releases, and consequently higher exposure, and fuel failure. The fuel failure will increase the radioactivity of the coolant and hence the radiation exposure to the workers involved in the maintenance or outages activity will be affected. So workforce workers get the highest risk, but are protected by the limits which are set by the national regulatory bodies from 20 to 20. And the public doses from NPPC are only the fraction of the limit, which is the 1 millisievert per year, usually 0.01 millisievert per year, far below from the background. So ICRP sets three principles for radiation protection: principle, justification, limitation, and optimization. Justification means that any radiation use must do more good than the harm. So electricity generation by the nuclear power must be beneficial than the risk posed by the radiation. Similarly, in the medical field, X-rays should be done only if they provide more benefit than the onboard. Limitation, although if the practice is justified, the exposure to the workers should not be exceeded from the legal limits. And optimization say that the doses to the workers should be ALARA, as low as reasonably achievable. So I'm going to start now from this was overview of the radiological protection principles and what is radiation protection at nuclear power plants. I'm going to start the very basics of the radiation protection. So ionizing radiation encountered at NPP, nuclear power plants. Basically, there are four ionizing radiation which are encountered at nuclear power plant: alpha particles, beta particles, gamma rays, and the gamma X-rays and the neutrons. Particulate radiation are alpha particles and beta particles, and the electromagnetic waves are X and gamma rays, which are located at the end of the electromagnetic spectrum. The penetration distance covered by these radiations, you can see from the slide. Alpha particles are the massive, they have positive +2 charge. They interact with the matter via Coulomb interaction, and they have got the highest ionization potential, which means that if ingested by the body, they will cause the highest damage. So, but luckily, in nuclear power plant, the alpha particles are contained within the fuel, which is cladded. And if there is no fuel failure, the effect of alpha particle is negligible during the normal power plant operation. However, if the fuel failure if the fuel failure happens, the alpha particles are ingested by the or inhaled by the radiation workers, they will cause the most damage. They can be stopped by a paper. Beta particles are fast moving electrons. They have -1 or +1 charge. Their ionization power is less than the alpha particles. They are directly ionizing as alpha particles. They can be stopped from few millimeter of plastics. Gamma and X-rays are basically massless particles. The difference between X-rays and gamma rays is that gamma rays are emitted from the as a result of nuclear reactions. So they have a different origin and they do not cause direct ionization, but they can produce ionization radiation by the means of photoelectric fat complex scattering and pair production like mechanisms. Then we are gamma rays are can be stopped by the high Z materials or the dense materials like lead. They are very effective against stopping these gammas and X-rays. Then there are neutrons, and neutrons are very the most penetrating because they because of the reaction cross section mean free path. They have great mean free path. They do not interact easily, but they are stopped by the water containing material mostly. Water is most effective against the neutrons, and since concrete contains some molecules of water and some high-Z material, so it can act as a shielding against the neutrons and the gammas as well. So these are the alpha particle characteristics. Their range is very short, about 1 to 2 inches in air. They deposit large amount of energy in short distance of time. The shielding, few centimeters of air can stop them. Sheet of paper can stop them. Dead layer of skin, outer layer can stop them. Biological hazard, no external hazard. Only the internal hazard exists if. And the prevention against them, protection against them is the contamination control, use of proper PPEs and rubber stations to spread the process. To ward against the spread of cross contamination. Major sources of nuclear power plants are obviously the fissile materials or fuels used. Beta particles, their short distance, 1 inch to 20 feet, their low LET shielding, plastic, glass, and safety glasses can stop them. Biological hazard depends upon the energy of the beta particles, internal as well as external hazard, both can occur. Their prevention, avoid direct contact with the sources, keep distance, wear safety glasses to protect lens of the eye. Major sources are tritium, strontium 90, carbon 14, which are pure beta emitters, and most of the activated Trojan products, which cobalt 58, 60, antimony, silver, zirconium, niobium, and magnesium 54, and iron. These are all beta particle emitters, which are encountered at nuclear power plants. Then we come to the gamma rays. Range in air is very far, easily go several hundred feet, very high penetrating power since it has no mass, no charge. Shielding can be done using concrete, water, lead. Biological hazard is whole body exposure. The hazard may be external or internal. This depends upon the location of the source. Protection is time, using time, reducing time in the presence of radiation sources, distance, and shading. Major sources include the activated Trojan products like cobalt, cesium, and antimony. So gamma shielding, we can see that, as I told earlier, that high atomic number materials are very good against the as shielding material against the gamma radiation. So lead, you can see only a few inches of lead can stop gamma radiation as compared to the wood, water, or bad soil. When we come to the neutrons, neutrons in air is very far, range is very far, easily can go several hundred feet, high penetration power due to lack of charge, difficult to stop. Shielding, water is the best shielding material against water, concrete, plastic. Biological hazard is whole body exposure. The hazard is generally external but becomes internal due to the internal deposition. Protection is time, distance shielding, and administrative controls like log, access control of the areas. When the nuclear power plant is operating, the exposure of neutron is limited to the reactor building, and reactor building when the normal power plant operation is normally closed. So this is the administrative measure to prevent against the neutron exposure. Major sources are the fission, which reactor core, which happens in the reactor core and the power when the nuclear power plant is operating. So now I will talk about the sources of radiation which produce these radiation. These sources emit alpha, beta, gamma, neutron radiation. The number one source is the reactive fuel and fission products. Number two is the coolant activation products. Number three is the activated corrosion products. So the reactive fuel, to produce 1 watt of power, there are 30 billion fissions per second required. 30 billion fissions per second are required to produce 1 watt of power. So in each fission, 2 fission products are produced. So you can imagine the amount of fission products produced in 1 second. That is why fission product inventory is the largest source of radionuclide in the primary system. Examples include iodine 131, xenon, krypton, cesium, tritium, and the actinides. If the cladding is intact, fission product released to the coolant is minimized. Coolant activation products and activated products hazard is dominant. If there are high levels of TAM material or fuel cladding failure, this will impact the. This is going to impact the fission product. Can be a significant contributor to the overall source term that radiation protection must consider in relation to the worker doses. That is only in the case of TAM material that is fixed on the during the manufacturing process on the fuel assemblies and the cladding failure. Number two, coolant activation products. The coolant activation of hydrogen and oxygen produces N16 and tritium. There are some chemicals injected into the primary circuit, like lithium is injected for the control of pH. Boron is injected as a chemical shim to control the slow reactivity changes. And sodium 24 is also present as an impurity. So activation of all these impurities, chemicals, and the water molecule itself generates the coolant activation products. So in general, these species are not a concern for worker-related doses, but they may be a concern related to effluents. Oxygen 16 contained within the H2 interacts with the fast neutron in an NP reaction, forming N16. N16 is one of the highest, if not the highest concentration radioactive constituent in the coolant during power operation. So N16 emits gamma. So the highest gamma activity produced in the reactor coolant is by the N16, while the maximum beta activity is produced by the tritium. The resulting high energy gamma released by the N16 is one of the limiting factors related to containment entries in PWRs and tribal entries and steam dependent entries in the PWRs. This is during the power operation, when the reactor is operating, N16 produces 6 MeV of 6 million electron volt of gamma, which is very high gamma. It can cause a lot of, it can cause huge exposure. So it is a limiting factor that the containment and reactor buildings and in the case of BWRs, rival and steam dependent entities are limited or controlled. This is the origin of the main activation products present in the primary coolant system from the primary coolant impurities of the reactor building. Activation products N16, reaction type, half-life, these are all mentioned. The most significant reaction here is the N16, tritium. Tritium, you can see, is produced from the chemical which are injected in the reactor coolant. Carbon 14 and argon 41, they do not pose hazard in terms of direct exposure, but they are concerned, more of a concern in the effluent releases from the plant. Sodium 24 and zinc are also produced as coolant activation products. Then we come to the third and last part, which is the activated corrosion products. Activated corrosion products are present the largest challenge to the plant personnel related to the source term. These can be divided into two sources: out of core corrosion products and the assembly material of fuel construction corrosion products. These longer-lived activated corrosion products are captured within the oxide layers of piping surfaces and create the radiation fields that workers are challenged within today's nuclear field. So this is the mechanism in a generic PWR process of corrosion product transport. If you can see the reactor, in the reactor we have reactor pressure vessel, which is made of carbon steel. Then we have silver, indium, cadmium alloy control rods. Then we have fuel, we have fuel clad. All the structure material of the reactor pressure vessel get corroded over the time, and since there are neutrons present in the reactor core, so they get activated, they detach and move to the primary circuit, where when maintenance is performed, the workers can get doses due to these sources. On the other hand, other than the reactor core, the other components like steam generators, reactor coolant pumps, and the pipes from which the reactor coolant flows, they are made of nickel, cobalt, chromium, iron alloys. They get corroded over the time, and releasing these radionuclides to the releasing these stable nuclides to the water. They move through water into the reactor core. They deposit in the core, become activated and resuspended, and activated corrosion products deposit on the surface outside the core, creating the radiation field. These are the two processes by which the corrosion products are produced. These are the corrosion products which are produced in a typical nuclear power plant. The main hazard comes from the cobalt, silver, and antimony radionuclides, because they have longer half lives, and they are hard gamma emitters. They emit gammas of very high energy. So to summarize, the contribution of radionuclides to the dose rates, overall dose rates, efficient products, limited impact on the radiation field unless significant fuel defects, number, size, or combination are present. Refueling operators are shielded from the very high and interstitial fields from the fuel assembly by the refueling cool water and distance. The most important radionuclides with respect to worker dose are the activated corrosion products like cobalt 58 and cobalt 60, silver, antimony, zirconium, and niobium in pressurized heavy water reactors. This is a summary of the text previously presented. Now I will move to the radiation dosimetry at the nuclear power plant. So what is radiation dosimetry? Radiation dosimetry is the measurement, calculation, and assessment estimation of the absorbed dose and assigning these doses to the individual. This means that the whatever changes are produced as a result of radiation exposure, we cannot measure them or observe them directly from our body. So we have to develop a quantitative relationship between those measurements which are made in the field and the chemical or biological changes that radiation would produce in the target. So this correlation, quantitative correlation between the measurements made in the field and the chemical or biological changes between the chemical and biological changes is called the radiation dosimetry. So radiation dosimetry depends upon the exposure type. There is external exposure and there is internal exposure. External exposure means that if the source of radiation is located outside the body, then it is called external exposure. And if the source of the radioactive material is deposited into the body, then it is called the internal exposure.
Mr. Hallett, sorry for interrupting you. Maybe if you can just wrap up to go with the Q&A session. Part of the topics that are not sufficient to cover during this presentation time, we will send your slides to the rest of the audience. And in case if they have further questions, maybe they can message to you. Is that okay?
Okay. Okay. Can I move to the last slide? Can I move to the last slide?
Yes, please. Thank you.
Okay. Okay. Sure. Okay. Future trends in radiation protection and nuclear power plants, AI for predictive monitoring, remote handling, advanced protective measures like smart suits, lightweight shielding provisions, and small modular reactors with inherent safety. These are the advances in future trends. Challenges are the decommissioning of old plants and climate resilience. Summary, key takeaways are RP at nuclear power plants relies on principles of justification, optimization, limitation, controls of design, dosimetry, chemistry, monitoring, administrative shielding, TDS, time distance shielding, and lesson learned to minimize risk from radiation sources at nuclear plants. Benefits are safe operation with those below natural background, international standards, and civil protection. Call to action is adhered to LARA for worker public safety. RP strives to make the NPP one of the safest energy sources. And these are the references or the sources which I have used for the preparation of this presentation as the IEA Safety Standard ESR Part 3, ICRP recommendations, OECD and NEA report on the source term management, WANO guidelines on radiation protection, and our national regulation, that is EPAC 904. Thank you so much.
Thank you so much, Mr. Mahmood. We learned a lot and you are very detailed. Thank you so much.
Yes.
If
Thank
anybody
you.
has a question, please put it on the chat or raise your hand and be called. We have just about 2 minutes, so please no long questions, just quick questions. Okay. Tamar said, what technological barriers prevent radioactive materials from being released into the environment? And another question from Najwa said, what are today's best international practices to ensure radiological protection for workers and nearby communities? If you can answer these, then we can maybe bring today's session to a close.
Okay. The first question, what are the technological barriers against the release of radioactivity? We have basically 3 barriers. Number 1 is the fuel cladding. We know the fuel assemblies are cladded, usually zirconium alloy. The first barrier is the fuel cladding. The second barrier is the reactor pressure vessel itself. And the third barrier is the containment structure. So these are the 3 barriers which are used as a barrier against the release of radioactivity to the environment. Regarding the second question,
The international practices.
Okay, the international practices, I think, sorry, can you repeat the question?
She said, what are today's best international practices to ensure radiological protection for workers and nearby communities?
Okay, so the best international practices rely on design features, optimization principle, that is basically ALARA, which is as low as reasonably achievable, taking into account the economic, social, and other factors. So the best practices are So the best practices are, and in terms of small modular reactors, we are making advancements in that, which will also improve the radiological protection aspects of the future trends in the RP.
All right, thank you so much, Mr. Mahmood. We learned a lot. We hope to see you all in the next session. I think it's tomorrow, same time, same venue on Zoom. Okay. Have a nice day and God bless you all.
Thank you. Thank you so much. Thanks for having me.
It's a pleasure.
Thank you so much, Ya, for moderation. Thank you so much, Aisa Diallo, the youngest moderator in this summer school. She is 24. It is another special network I create with under 25. I see she's teenagers in nuclear. Teen in nuclear. Thank you so much. I thank you, the different speakers, and I let Florencia to conclude in the great word. Thank you so much.
Thank you very much, Lancina. Thank you very much to all our distinguished speakers, moderators, and wonderful attendees for today's session. So we just want to remind you that each of these programs is a testament to power of global collaboration. And today, as we dived into topics like radiological protection and the future of nuclear energy in Africa, we are reminded that nuclear science is not confined to labs or textbooks. It's a living force shaping our health, our environment, and our shared future. So the summer school is a space where ideas cross borders, where students and experts from every corner of the world come together to learn, challenge, and inspire. So it's a place where innovation meets purpose. So let's continue to ask bold questions, share our unique perspectives, and build the kind of knowledge that doesn't just inform you, it transforms you. So thank you very much for today, and we wish you to have a very good rest of your day, depending where you are. God bless you. Thank you.
Thank you. Bye.
Hi, thanks so much.
Thank you. Thank you for today, Dora and Mr. Enabot. Wonderful. Yeah, Isata. Thank you very much, Mr. Halid. We really appreciate your entire support.
Really good job,
Thank you.
Florencia, and the entire team, Lancina,
Great.
and everyone else. Brilliant.
Thank you so much, Dora, for your wonderful support. We hope to see you for the next edition as well.
All right. Bye.
Bye. Take care. Thank you.